Assalamualaikum. Welcome back to Circle Labs Physics Tutorial for high school students. Today's episode is a revisit of capacitor with a dielectric. What effect does adding a dielectric have on the capacitance, potential difference, and induced charge in the capacitor? Join me till the end of this video. Watch and learn. The question is, the two plates of a parallel plate capacitor each have area 0.460 meters squared, are 3.00 millimeters apart, and initially have vacuum between them. A power supply is attached to the capacitor, charging it to 4.00 kilovolts, and is then disconnected. A dielectric sheet is then inserted that fills the space between the plates. The potential difference between the plates decreases to 2.50 kilovolts, and the charge on each plate remains constant. Fine. Letter A, the original capacitance. Letter B, the charge on the capacitor plates. Letter C, the dielectric constant of the dielectric. Letter D, the new capacitance after you insert the dielectric. And E, the magnitude of the induced charge on the faces of the dielectric sheet. In the figure, we have a schematic diagram of a parallel plate capacitor in a vacuum. And when the same capacitor contains a dielectric, each plate of the capacitor has an area, capital A equals 0.460 meters squared. And the power plates are distance or have a distance of separation equal to uh, 3.00 millimeters. And they initially have uh, a vacuum, all right, between the plates. A power supply is attached to the capacitor, charging it to an initial voltage or potential difference V naught equal to 4.00 kilovolts, and is then disconnected. The electric sheet is then inserted that fills the space between the plates. So the potential difference between the plates, all right, decreases to uh, V equals 2.50 kilovolts. Target variables in this problem, we have in letter A, the original capacitance, denoted by capital C naught. In part B, the charge on the capacitor plates, denoted by capital Q. In part C, we have the dielectric constant, denoted by the Greek letter kappa. D, we have the new capacitance after you insert the dielectric, that's denoted by capital C. And last but not least, in part E, we have the magnitude of the induced charge on the faces of the dielectric sheet. Okay, this is denoted by capital Q's of I. For our computations, starting with um, finding the original capacitance, capital C naught, which is computed by just multiplying the constant epsilon naught, or we call this uh, permittivity constant, and then multiplied by the area of each plate, capital A, and divided by the separation distance between the two plates, D. That is, capital C naught equals 8.85 times 10 to the negative 12 farad per meter times 0.460 meters squared, and divided by 3.00 times 10 to the negative 3 meters. So when we do our math, we find the original capacitance, capital C naught, equal to 1.36 raised to the negative 9 power farad in three significant figures. Part B, we are to find the charge BQ, and it is simply the product of the original capacitance, C naught, and the original potential difference or voltage, V naught. That is, big Q equals 1.36 raised to the negative 9 farad times 4.00 times 10 to the third power volts. So multiplying these quantities, we get the charge big Q equal to 5.44 raised to the negative 6 coulombs, also in three significant figures. In part C, we are required to determine the dielectric constant, kappa, and it is simply the ratio of the original voltage V naught over the new voltage V. That is, kappa equals 4.00 kilovolts divided by 2.50 kilovolts, right? So we get the value of kappa equals 1.60, also in three significant figures. Part B, the new capacitance, capital C, after the dielectric sheet has been inserted into the capacitor, okay, is just the product of the dielectric constant kappa and the original capacitance C naught, or big C equals 1.60 multiplied by 1.36 raised to the negative 9 farad. So multiplying these two quantities, we get the value of the new capacitance, big C, equals 2.18 raised to the negative 9 farad. And last but not the least, in part E, okay, we find the induced charge denoted by capital Q's of I, and it's just equal to uh, the big Q, which we had just computed earlier, multiplied by quantity 1 minus the reciprocal of kappa. That is, big Q sub I equals 5.44 raised to the negative 6 coulomb times quantity 1 minus 1 over 1.60. Doing our math, we get the value of the induced charge capital QI equals 2.04 times 10 to the negative 6 coulomb, also in three significant figures. We can also evaluate the results of our computations. We say that inserting the dielectric increased the capacitance by a factor of kappa, which we found to be 1.60, and reduced the electric field between the plates by a factor of 1 over kappa, or 1 over 1.60. It did so by developing induced charges on the faces of the dielectric of magnitude big Q sub I equal to 2.04 raised to the negative 6 coulombs. Before we end, let us emphasize the key concept that we applied in this problem. Adding a dielectric with dielectric constant kappa that fills the space between the plates of a capacitor increases the capacitance by a factor of kappa. For a given amount of charge, adding the dielectric also reduces both the potential difference or voltage between the plates and the electric field at each point by a factor of 1 over kappa. And that concludes our tutorial. Till the next episode, mabuhay. Mashallah. Thank you very much for your indulgence. Please don't forget to subscribe to my YouTube channel. Alhamdulillah.